So my name's OJ. I go by the name The Colonial, and I'm here to talk to you about the guts of Meterpreter. So I had a couple of personal goals when putting this talk together, and the first one is to try and get rid of the myth that Meterpreter is like black magic and that it's hard to build and it has all these really obscure things that it does that no one understands. It's actually really, really simple. It's just been a little bit difficult to contribute to for quite a while. So I want to do that. I want to show you how things work internally in a couple of scenarios and hopefully inspire a couple of you people who know a bit of C or whatever to dive in and contribute something of your own. So I'm going to go through what Meterpreter is, or at least what I think it is. There seems to be a few different definitions. The bits and pieces that make it up, particularly from a comms perspective, and how you might sort of use that if you were adding or extending it. And then go through my favorite feature, which is migration. By the way, who's a pen tester in here? Show of hands. Oh, lots of pen testers. So who uses Metasploit? Who uses Meterpreter? I love you guys. Yeah, awesome. Okay, so and then hopefully at the end we'll have time for questions. But I've got a lot to get through, so I might talk a little bit quickly. But throw questions at me along the way if you like. I'm happy to take a Nerf bullet if it adds context for you. All right, so what is it? So back in the day when everyone was popping shells, everyone loves shells. Shells are really good, but they don't necessarily give you everything that you want to do when you've got the chance to do post-exploitation. So that's where Meterpreter comes in, or the meta-interpreter. Who knew that it was the meta-interpreter? Yeah, I didn't know that until about a week ago either. So it's the meta-interpreter, and it's kind of it's a payload, it's a rat, it's good if you're a pen tester, it's bad if you're a victim. It's a multi-platform tool. Comes in a variety of flavors. It's running on Windows 32-bit, 64-bit. There's Java versions, there's Android versions, and we're really close to having an OS X version running as well, which is really cool. The goal of Meterpreter really is to be as forensically silent as possible, so don't write to disk and hide itself in memory and encrypt communications and all that kind of stuff so that if something does go bad or you have incident responders trying to track you down, it's not a particularly easy thing for them to do. You actually have to scan memory to find it. Gives you a lot more control as compared to a normal shell. Gives you really good sort of things like pivoting. Gives you a bunch of post modules that come with Metasploit. And yeah, it's a lot of fun. All right, so it's huge. Like the code base is huge. There's 5 or 6 different versions. Can't possibly cover all of them in this talk. In fact, I wanted to sort of add 3 or 4 more bits to the end of this, but yeah, there's no way I was going to squeeze it in. So given that there are so many different implementations, I kind of had to choose one, and I chose the one that I know the most about, and that's the Windows version. So what I'm going to be covering is mainly x86, Win32, but a lot of what I talk about will map pretty much directly to 64-bit, and some will map to POSIX, but all the other ones are actually very different. So, but dive into the code bases and have a look, because they're really interesting. All right, so the main bits that it's made of. First bit is C and C++, which everyone loves. I know I love it. Who loves C++? Ah, he admitted it publicly. Fantastic. So yeah, there's a lot of C and C++. So if you're going to contribute to at least the Windows or POSIX Meterpreters, you're going to be diving into C and C++ land. There's also some sprinklings of assembly, both on the MSF side and on the Meterpreter side. But and the good thing about it is that the assembly is not even inline. It's just blobs of shellcode. So if you want to fix that up, be my guest. And then finally, a good dose of Ruby. I really love Ruby. Not really. But the only reason I mention it is because obviously Metasploit is completely written in Ruby, although it used to be in Perl. And you'll probably see sprinklings of all 3, or you will see sprinklings of all 3. A little bit of Ruby, a lot of C, and a dabbling of dabbling of assembly. So rather than just sort of throw code in your face without any context, what I wanted to do was run through a scenario that I think everyone who's used Meterpreter before has probably seen. And that's establishing a session using reverse TCP. So this is our tried and proven MSO 8067, which unfortunately will probably die a death sometime soon. So here what I've done is I've configured Metasploit to point to an XP box that's vulnerable to this bug. And we're sitting there ready to go, and all I need to do is type exploit. So when I type exploit, in this particular case, Metasploit kicks up a listener on the port that I've asked, so 4444. And it sits there, and the next thing that it does, at least in the case of this exploit, is it fingerprints the target. So not all exploits do this, but in this case, it's poking the SMB service that's sitting on 445 on the XP machine, and it fingerprints it a little bit and says, okay, well, I've detected that this is XP SP2 and it's got NX enabled, that kind of stuff. But you won't necessarily see that in every exploit. And then after that, it attempts to trigger the vulnerability. So what it's done there is it's generated some shellcode, and it's hurling a big buffer at the target. And hopefully, you're going to end up with a Meterpreter session. But to really understand, and this is the point of this talk, what's going on here, we're going to dive just a little bit deeper. So here's the scenario, right? We've got our attacking machine running Metasploit on the left, and our target machine running the vulnerable SMB service on the right-hand side. So that's sitting there listening on 445. And we on our side have our exploit ready to go. So when we kick it off, we fire up our listener on our port, and then we connect to that service on 445. Now at that point, some functionality runs, and the socket sort of delegates responsibility to a function which has a buffer sitting on the stack, and immediately after that buffer, you've got a return address. Pretty basic exploitation stuff here, right? So we send a buffer that's way too big, and we overwrite the return address with something we control, and the goal is to sort of change control flows so that our own shellcode gets executed. Now, there's a lot of magic that kind of goes on there. There might be ROP chains and various other things, but that's kind of beyond the scope of this. And from there, that shellcode's going to connect back to our listener. All right, everyone's sort of seen this happen before, right? It's pretty simple stuff. Okay, so then what you see in your console is this message saying sending stage. Now, sending stage, like there's a number of stages involved in this process, but again, I kind of want you to know what that stage is and what it's made up of. So again, I'm going to go deeper. Now, the first stage after shellcode consists of a DLL called metserv. Metserv is kind of like it's the first thing that we send up. It's minimalistic, and the goal is to sort of establish secure communication so that we can do more. What it does is Metasploit will take a copy of that off disk, and it'll generate a little bootstrapper, and it'll overwrite part of the DOS header with that bootstrapper, and then send it up, amongst a bunch of other things. It sends it up to the target, and the target executes it. It bootstraps and does a bunch of other magic. Now, in the case of HTTP or HTTPS payloads, which this isn't what we're going through, there are other things that it patches as well, so that when it kicks off, it knows sort of how to connect back. But that's kind of not too interesting in this particular case. So I love assembly language. You're probably going to see a little bit more of it during this talk, which I apologize for. But this is effectively the stub that gets overwritten, that overwrites the DOS header. And the first thing it does is it just tries to figure out where it lives in memory. So there's a bunch of different techniques in which to do that. So that's all it's doing. And then the next thing it does is it attempts to run something called the reflective loader. Now, you'll notice that here we've got, which one is it, EDX? EBX. EBX becomes a pointer to where we are in memory, and we need to know, based on where we are in memory, where the reflective loader is, so we have an offset stashed somewhere. So these question marks here are a value that's actually written to this shellcode by Metasploit. So Metasploit will look at the DLL, pull out an offset to reflective loader, punch it into the shellcode, send it up, and so when this executes, it knows where to jump to. So that's exactly what's happening there. So what is the reflective loader? Who knows anything about reflective DLL injection? You might be bored. I hope you won't be bored. This is really, really cool stuff. All right, so this guy, Stephen Fewer, he's a bit of a machine, this guy. He's based in Ireland. He runs his own company called Harmony Security. He's the guy that came up, at least with this implementation of reflective DLL injection. So RDI is it's kind of like a mini in-memory PE loader that doesn't do things that like the load library API does. So it doesn't read from disk. It pulls things straight out of memory. It doesn't register any of the DLLs that are reflectively loaded with the host process. So things like sysinternal tools can't figure out what DLL has been loaded. So again, in an effort to sort of not be visible. And in our case, we've made a couple of small adjustments to RDI to make it live nicely within the MSF ecosystem. All right, so I'm going to go through it, and I'm going to show you the code. Please just bear with me. There's a couple of bits in there that are a little bit tricky, but it's worth it. All right, so the steps are, the first thing we need to do is, well, we've been pushed up to a remote target. We don't know where we live in memory. So we've got to figure out where the start of our image is so that we can go ahead and reflectively load it. After that, we need to iterate through the process environment block and get access to help DLLs and functions that we can then use to sort of do more interesting stuff. And once we've done that, we need to allocate some memory and prepare it for where this new image is going to go. And then we import all these functions manually. So we're kind of doing what the operating system does for us when we load library. We deal with all the relocations thanks to PE files not handling position-independent code. And then finally, when it's loaded, we then invoke DLL main, which is the entry point to a Windows DLL. Okay, excuse me. All right, here we go. This is the fun stuff. All right, so first of all, we're going to find the image's location. And this is what it looks like, or at least a cut-down version of what it looks like. So this first call here, caller, is actually a macro that wraps an intrinsic function that literally says, what's the address of the thing that called me? Now, if you kind of remember back to our RDI stub before, when we were calling this function, we were actually right at the start of the bootloader, the DOS header, right? So we kind of figure out where that calling address is, and then we start iterating backwards to find the start of the image. So that's what this next bit does. It's saying, have we actually stumbled across something that looks like a DOS header? And then once it's found it, there's an edge case, at least in 64-bit mode, where we might actually end up looking at something that's not a header, so there's an extra check. But then afterwards, we look for the NT signature as well, and we kind of assume that if at that location there's a DOS header and here we've got an NT signature, then we're good to go. We found the start of our image. And so this library address here is the value that we know is the start of our image in memory. Okay, so with that in place, we want to go through now and pull stuff out of the environment so that we can do things like get proc address and load library ourselves. So this code is a little bit quirky. This first part here, so in Windows, 48 bytes off from the file segment is the process environment block, and that's just a bunch of descriptors that can contain metadata about how the process is running and what libraries are loaded. And so from there, we can get an offset to this bit of pointer arithmetic, and we figure out exactly where the import address table is. And from that import address table, we're going to be able to find things like kernel 32 and user 32 and all those other libraries that have really useful functions. And so moving on, again, once we've got that pointer, we want to run through the table, and we want to figure out exactly which libraries have been loaded and find the ones that we're interested in. But in order to do that, we need to be able to identify those things. So what we're doing here, we get our pointers to the start of the import address table, and we start looping through it. Now sorry, just going back a sec. These two things here, this is the name of the DLL, so kernel 32, and this tells us the length of that DLL name because this is a Unicode buffer. It's not ANSI, so it's not null terminated. From there, we do a little hash. When I say we, I mean Stephen. Stephen does a little hash. And what this is doing, it's a really simple hashing algorithm, and it's got some pretty crazy properties, like hashing all of the modules, or at least all of the base module names across Windows that are common to all the operating systems, doesn't result in a clash, which is kind of cool. And the same goes for function names within those things. So it's really simple, but it's a really easy way of identifying a function or a module name just by running this little algorithm. It's just kind of like a rotate 13 bits, pull the next value in, add it, rotate 13 bits, etc. So that gives us a hash value, which we can then use later on. Now, the reason why we do this with hashing instead of saying loading strings is, so strings are pretty big, they're null terminated, they bloat payload size, and part of the goal for this was to make the hashing algorithm and the process that's used to locate functions in memory very similar to something called the block API, which is another thing that Stephen Fewer created that lets you do similar sort of stuff in shellcode. So anyway, having a 32-bit hash in memory is obviously a bit of a savior as compared to having dozens of strings of functions that you're really interested in. So that's why we hash. Anyway, once we found a valid hash, so here we've calculated the hash in value C, and then we compare it to our known hash for kernel 32. That's a DLL that we're interested in. And from there, more magic pointer arithmetic. And really all this is doing is saying, okay, I've got the module. Now I want to go and find all of the functions that are exported for that module, and we're going to start iterating through those. Nothing too tricky. Okay, now once we've found that address table, the module table, we're going to calculate the hash for each individual function within that module. And that will be things like load library and all those other functions. So Once we've got that hash value, that hash algorithm is exactly the same as the one I just described before. This is in a helper function because these are ANSI strings, and hence we don't need to worry about lengths. So we've got a hash, and one of those values is one that we're going to be interested in. So once we've found a library we're interested in, the next thing we do is we get the address of the function itself, which is not particularly fascinating. But here what we do is we say, okay, well, if this hash points to this function, then what we want to actually do is we want to patch, or we want to take a copy of that address and cast it to a function type that we know we can call. So you see there's just a couple of casts going on here. We know that this, in the case of load library, is going to be the load library function. So we've got our own sort of type def that says, well, that's a function pointer that takes a bunch of types. And so we cast that value to some particular type, and then we stash it so that we can use it later. And we do that for a number of functions. I've only just shown a couple here. You can see the rest in the code if you're interested. So we've got all our modules. We've got all our functions that we need to use to do more PE loading. And so from now on, we can start using those functions to do more interesting stuff, like creating a valid PE image. So the next thing we want to do is we want to allocate some memory and kind of move things over. Anyone familiar with PE loading already? Same guy? Okay. So the PE image requires a certain sort of layout in memory, and the size on disk isn't necessarily the same as the size that it needs to be in memory. So that's why we can't assume that the DLL that we've already pushed up is kind of okay to use where it currently is. And so we need to sort of allocate memory, move it over, and make sure there's enough space for each section and deal with relocation. So that's the reason why we're doing this. Plus, the memory we may have just been written to, at least to a point, may not be executable. Right, so what are we doing? We're going to do some more pointer arithmetic to get a pointer to a location in memory that tells us where the image is that we're going to be loading. And then from there, we're allocating space. The only thing that's really worthy of note here is that we're making sure that the memory is executable, readable, and writable, so that once we've actually copied everything over, we can just kick off a thread and it'll go ahead and execute happily. And here you can see, slightly off screen, that we're specifying the actual size of the image, not the size of the file on disk. So we should have enough space in which to put everything in. And then from there, this is this very slight enhancement that we do with Metasploit that isn't in the original RDI implementation, and that is we request with the operating system that the memory space that we've just allocated does not ever appear in the page file. So if you've got that quirky scenario where you've just been paged to disk and then the OS crashes and then incident response kicks in, like you're going to be in the page file, right? We kind of don't want that to happen. So this function call allows us to do that. However, the documentation says, well, you can ask us to do it. We're not necessarily going to guarantee that you won't appear on disk. But for the most part, I mean, I haven't seen it. Don't know whether you guys have before. So that's one of the things we try and do, again, to try and stay off disk. And then from here, we just do a byte-by-byte copy of the existing PE header, including the patched DOS header, which Windows generally doesn't care about anyway. So that first part is then moved over to the new memory block. Now, when that's done, I'm going to rip through and do the section. So there's not really that much tricky stuff going on here. We calculate various bits and pieces about the section, including its size, that it should actually be in memory. We pull out the number of sections, we iterate through each one, and again, we're doing a byte-by-byte copy. So size of raw data rather than the size that it is on disk. Basic pointer stuff that figures out virtual addresses based on the offset for the start of the image, and then we just copy it over. And by doing it this way, we end up allowing for the space for each section rather than it just being the size that it was specified on disk. Is that clear so far? Yep. Okay. Okay, so from here, we've got this DLL sitting in memory, but it's obviously got some dependencies. Those dependencies haven't been loaded, so if we attempted to run the DLL now and it attempted to hit the IAT and run a function, it would crash because it doesn't actually have a valid address. So we need to go through now, and for each one of the values in the import address table, we need to go and find the module and the function that it's looking for and manually wire that in. So here's where we start to figure out exactly where the import address table is. And again, more magic pointed stuff that points directly to the VA for that table. And then while we actually have a valid entry that we're looking at, what we do is we call load library on the entry. So again, we pulled load library out when we did our sort of process environment block iteration before. So we have that function, we've got a valid function pointer, and now we're going to load that library from disk based on its name. That's just a little bit of error checking to say, well, if we couldn't load it, we'll just carry on and hope that nothing dies later on when a function's called. And so from there, there's two different ways in which a library can be sort of linked with a DLL. And one of them is by ordinal only, which is just like an offset into a function table list. And the other one is by name. So this is catering for both cases. It's checking to see whether the ordinal flag is set. And from there, again, just a big bunch of pointer arithmetic. All it's doing is it's offsetting based on an ordinal into a table of functions, figuring out a virtual address based on where that is currently in memory after loading it into memory. And then you'll see down the bottom here, we actually patch the current value, which is inside the import address table in our current module, with the value that we've just calculated based on loading the new library into memory. So we're literally just going, okay, we're going to rip through, we need load library, or we need kernel 32. So let's load that up. Load it into memory, we're going to find a module within it and wire that function pointer in, and then slowly but surely, as we've gone through all of the table, hopefully we'll end up with an image that has all of the IAT entries, so that when we kick it off, it's not going to die. This is the less interesting one, and much simpler. So in the else case, this is when we do actually have a library name that we can load. As you can see, we get the name, the address of the name, and then we call getProcAddress. So getProcAddress says, for this module, tell me where I can find this function by name, and it will return a pointer. And we use that pointer again to patch straight into the IAT so that we can call it later on. Pretty simple, right? Right, so with that in place, the only thing really that we've got left to make sure that the PE isn't going to crash is dealing with relocations. Relocations, anyone know what relocations are? Yep, same guy. Yep, okay, so the PE image doesn't really support the idea of having position-independent code. What it has is a preferred base address and a bunch of functions that kind of call based on that return address. But if Windows isn't able to load that library into that exact address, what has to happen is relocation. So wherever it is based, a bunch of offsets and calculations happen, and each individual call is patched. And this is kind of what it looks like in pseudo kind of form, because the code around this stuff it's very hard to put on a slide and not have you walk out while I'm talking about it. So really, in theory, all it's doing is there's a bunch of relocation block entries. And inside those relocation blocks, there's detail of individual relocations. And so we just do a double sort of for loop, and we iterate through. And based on the address that we started at, and we look at the preferred address for the image, basic offset, and we rip through all the relocations and either add or subtract a value based on that offset. And that's really all it does. It just looks a little bit messy, hence the slide. So when that's in place, we now have a completely valid DLL sitting in memory that we can invoke that hasn't been registered with the host process and hopefully will never touch disk. Okay, so we then invoke DLL main. So we want the DLL to be initialized. Excuse me. And so we figure out the address of the entry point based on the metadata in the header. And once we've got that pointer, we call DLL main with DLL process attached. So we're back in sort of standard dev land now. The DLL is kicking off exactly as it should. But because we need to actually deal with DLL main in other scenarios due to MSF, we also return that function pointer back to the bootloader that we looked at before. So we're kind of back here now. So this call here is what we've just executed. And we come back out of that, and so DLL main's pointer is in EAX, where the return value comes from, and we stash that in EBX, the EBX register, which doesn't get trounced when you make other calls, right? So we've now got a persistent location for DLL main, and we'll be calling that a couple more times. So the first time, this is Metasploit specific, in case you didn't notice. What we're doing is we're taking a copy of the socket we're currently doing communications on, which is sitting in another register called EDI. We take that, stick it on the stack, pass some Metasploit attached, so all of the components of Metasploit, including metserve and a bunch of other extensions, will look for this and handle functionality based on that rather than just doing it as part of process attach. So this is actually a blocking call. In this case, we're invoking metserve, that first stage, and metserve is going to take the socket descriptor and handle communications from there on. It's going to wrap it in SSL and do a bunch of other bits and pieces. And so this blocks until you've asked Meterpreter to shut down, or it crashes, or incident response manages to shut you down. And when that finishes, it will come back, it'll come back here and call Metasploit detach. Now, when you're setting up an exploit in Metasploit, you guys are probably familiar, you specify in your payload what kind of exit functionality you want. So if you know that your exploit is smashing an SEH vulnerability, then you've got the ability to say, well, this is an SEH exploit, I want you to exit in this way. If you know that you're running in a separate thread, we just want to terminate the thread so that the process doesn't crash. So that's what this exit functionality actually is. And again, this is patched in by Metasploit in the shellcode prior to that little bootstrapper being uploaded. Okay, so there's more fun stuff in Metasploit attach, and we're going to go a little bit deeper again. Okay, so we're running metserve. We're in DLL main. The first thing that we do is we create a server thread. So there's this thread running behind the scenes, and when we get a command that's been sent from Metasploit, that's the thread that's going to execute the command. On top of that, we take over, as I said, communications. We fire up an OpenSSL, and we make sure that everything's encrypted from there on in. That's recently been patched by Todd Beardsley so that it's not susceptible to client-side heartbleed attacks, which is cool. Once that's in place, we then kick off something called a scheduler. So those familiar with Meterpreter will know that you can do things like interactive shells, or you can do port forwards, and a bunch of other cool things that kind of run behind the scenes. That's handled by the scheduler. So that's when that's initialized, and then from there, once those two threads are running and they're doing their thing, we kick off something called the dispatch loop, which is kind of not too dissimilar from a Win32 message pump. We're just listening on a socket instead. Okay, so we're sitting there waiting for messages from Metasploit to come in. So is that it? Not quite. We're almost there. The only problem that we've got now is that while we've got comms up and it's encrypted, we don't have any functionality that we can use. And the reason for that is because metserve doesn't have anything else in it. And the goal there is to make that first stage as small as possible so that we can establish comms, and we've got less stuff going up in the clear so it can't be fingerprinted or caught by IDS or anything like that. So what we need to do is we need to push up more stuff that gives us the functionality that we're looking for. Okay, so anyone ever got to this point here and run a command and it said command not found? Yeah, lots of people. This happens all the time. It's one of the most common questions, right? Why is it that it says I've got a session but it doesn't? So at this point, metserve is running, but you don't have any commands. So if your connection's really laggy, or for whatever reason it takes a while to upload the next bits, you can be sitting there saying, you know, get system, get UID, or whatever it happens to be. But the components haven't been loaded, and that's why it doesn't work. So if you wait a little while and try again, it will probably work, except when it doesn't. All right, so we'll go deeper into this again, I think. All right, so there's two components in the Windows world, Standard API and Priv. Now, Standard API also lives in all of the other Meterpreter implementations, but Priv is something that's specific to Windows because there's Windows-specific privilege escalation style stuff. So the guts of the get system command, which I'm hoping everyone loves, lives inside Priv. So the guts, when I say the guts, I'm talking about the basics like who am I, where am I running, file uploads, file downloads, that being able to open a channel just to send data back and forth, that kind of stuff. That's exactly what Standard API gives us. And so what happens in the Windows sense is we get our Meterpreter session running, and then Metasploit straight away sends up a copy of Standard API and then sends up a copy of Priv. Now, these two are officially extensions to Meterpreter, which you guys will go away and create your own, I'm sure. And so in order to do that, you need to know a little bit about how it works. So every extension needs to have this table of commands that they support. So here, I mean, who's familiar with Railgun? Railgun's awesome. Love Railgun. So Railgun is pretty amazing, but I won't dive into that now. This is basically just saying, I'm going to take this identifier, this command, and I'm going to associate it with a function pointer. And so what happens is when the extension's loaded, this function here gets invoked by metserve. And here we're just calling command register all on that array of commands that we had. So that's turning around to metserve and saying, here are all the commands that I currently support as my extension. And it'll rip through that list, wire in a bunch of function pointers, and then effectively it's established and ready to go. So then if you type in get UID, that's when it'll be able to look up that identifier in the table and execute the function. So that's why you can get that little bit of disconnect. So it's pretty simple to get it wired in, right? So going back to our exploitation scenario, we've called back, and down here the first thing we're going to do is send up a copy of metserve. So we copy the binary over with a bit of patching, and then it's reflectively loaded so that it actually becomes a valid PE in memory. And it's taking over communications, and we're sort of established. And then from there, standard API goes over, reflectively loaded, priv goes over, reflectively loaded, and then from there, you're actually finally ready to go. So from here, you can load incognito, more plugins than you can poke a stick at. They have really, really cool functionality in there as well. So that process for loading is the same when you type in like use incognito. Pushes it up, gets patched, reflectively loaded, commands get wired in, bang, off you go. Make sense? All right. Are we there yet? Yes, we're finally there. You actually have a fully functional Meterpreter session. So now my job when I first started working on this was obviously to understand that. And recently someone submitted something to sec reactions that really summed it up for me, and it looks like this. You guys seen this before? All right. So I've been doing this for 9 months now, and I still feel like dancing every time I see a session open. It's fantastic. So like for us now, when we type, exploit and off it goes, there's actually a lot of magic that goes on behind the scenes. So next time you get shells, I want you to, sweet. Yeah. I'm tempted to just leave this slide up for the rest of the talk, because people will think that you're laughing at me when you're not. All right, so I'll put this back on at the end. Okay, so now you know how Meterpreter actually gets into memory. It's running. You're kind of hopefully avoiding detection. What I want to do now is dive into migration. Everyone's used migration, right? Yeah. So migration is a really fantastic thing. And me as a dev who's only recently joined security was kind of blown away by the idea of this thing. It's by far my favorite feature for what it does, and it allows you to jump across process boundaries. It's really, there's no other way of summing it up. But the fact that it doesn't drop connectivity is the thing that really gets me. I just think it's awesome. So the good thing about this is, like, you might have popped someone's browser or some other buggy third-party app which is unstable as a result of exploitation, or for some other reason you just think you're living in a host process that isn't going to last very long. The last thing we want is for that user to shut that window down and kill off your Meterpreter session. So what we want to be able to do is jump somewhere else without making the noise of setting up new connections and all of that other stuff, just so that if they do decide to shut it down, it doesn't matter. You've still got a bit of persistence on the box. All right, so we'll run through it a little bit again. Here's me just running the sysinfo command so you can see I'm running on the same XP machine that I was running on before. It's a Win32 instance. I'm running as a pleb user, and this is our process ID, 3548. Just to prove that this is running under Internet Explorer, you can see 3548 here, and it's Internet Explorer, so I'm kind of simulating that I've popped someone's browser and they may actually close it. Or if they've been phished, they might go, wow, I probably shouldn't have clicked on that, so I'm going to close the browser down. So what I want to be able to do is move to something that's probably going to persist a little bit longer than Internet Explorer, particularly IE6. And that is look for explorer.exe, which is going to live for the life of the user's logon session. As you can see, the process ID is 1820. So from there, what I want to do is I type in migrate 1820. You sit there for another minute or so, depending on how fast your connection is. And at the end, it just says done. This is why I didn't demo this, because it's not a really impressive demo, is it? But as you can see, we have actually migrated. Our process ID is now 1820. So I've used this so many times, and I'm hoping you guys have too. But despite that little bit of time, a lot of crap's gone on behind the scenes, which I think is really cool, and that's what I'm going to show you. So again, we're going to go deeper. So this is the step, or the number of steps that we go through when we're doing migration from the Metasploit side. So on the Metasploit side, when we type migrate, the first thing we're going to do is check for the basics. Am I migrating to myself? Because that's pretty stupid. Do we have permission to actually modify memory space of the target process? Because if we don't, then we're not even going to attempt to do it. We're going to figure out what the target process architecture is, because migration allows you to jump from 32 to 64 or 64 to 32, and it caters for all the different scenarios for you. But in order to do that, we need to know what we're migrating to. Once we've done that, we figure out, or we generate a new payload that is specific to the architecture of the process that we're going to jump to, and that gets shipped up. So that's why there's that little bit of time at the start. When you type migrate, it's actually sending metserve up again. And we have to do that because we can't sort of copy ourselves out of memory because we might be changing architectures as we're jumping across process boundaries. So once that's done, we then send a command which contains the target architecture, the ID of the process, and the payload, ship that up, and then it's time for Meterpreter to take over. On this side, we sit here and we wait for migration to finish. We get a signal from Meterpreter, and then we just carry on as we did before. However, the interesting thing at the end, which again I really like, is it keeps track of all of the extensions that you had loaded prior to doing migration. So if you were running packet sniffing or something like that, it will push that extension up for you. So your whole session just kind of shifts over. It even carries over port forwards, which I think is pretty nifty too. So a bit of code, Ruby. Nothing really mind-blowing here. We make sure that when we attempt to open the process, we'll get a handle to a process object in Ruby. And the first thing we do is did we get one? Does it actually exist? If not, we bomb out. The next thing we check to see if this is a little bit of a hack, because if the architecture flag of value inside this dictionary doesn't exist, it means that we weren't able to read metadata out of the process, which implies we don't have permission to do what we need to do. So that's what that's doing. And then finally we're going, is it me? Whoops, is it me? And if it's me, don't migrate to me. That's a pretty stupid thing to do. A little bit more Ruby. So what we're doing here is based on the architecture, we're figuring out a new payload, and we generate this little class in memory that's able to sort of produce a new bootloader and a new copy of metserve that is going to function inside the target process. And when that's done, kind of instantiate it, because you know how Ruby works, right? It's if it looks like a duck and quacks like a duck, it's a fish. Yeah? So we're kind of creating a hybrid fish in memory before we create an instance of it. And then once we create an instance of it, we say, use this copy of metserve and then go and generate a blob of binary. So this stuff down here is just a big blob of shellcode that's been patched. Okay, finally, we're getting close now. So what we need to do when we create a request that's going to be sent up to Metasploit, there's this packet object, and there's a create request function. And the first thing we give it is the identity of the command that we want to run. So this could be a railgun thing, it could be migrate, it could be anything. In this case, obviously, it's migrate. So we create an instance of this request packet, and then we need to wire in values that are going to be sent up to the target. That's what these TLVs are. Now, it took me like 6 months to figure out what TLV actually stood for, so I'm going to save you the pain. And I'm going to explain it by going a little bit deeper. So TLV stands for type, length, and value, although the first part is a little bit misleading because the type also contains the identity of the value that we're pushing up. So after that, so that's a 32-bit value. Regardless of what architecture, that's a 32-bit value that gets written to the packet first. Immediately after that, there is another 32-bit value that specifies how long the data is that is part of this TLV. Okay, so in the case of, if I'm sending up an integer, that's 32 bits. If I'm sending up a Boolean, it's probably 32 bits again. If it's a string, then I'll calculate the length of the string, and that's what will get written to the length. And then immediately after that, the value is what gets written. And so the packets that get sent across the wire inside Meterpreter and Metasploit are literally just a header followed by a TLV, and then the next TLV, and then the next TLV. And it was kind of like a simplest thing that could possibly work. You read 4 bytes, and you know its type and identity. You read 4 bytes, you know its length. Once you've got the length, that's how many bytes you read, and then you're at the next TLV. You rinse, repeat. It's pretty much how you get the data out. In the case of migration, this is what they're defined as. This isn't too interesting, other than I just wanted you to see how an identity is made up of a type and a unique number. So when you guys are going away and building your extensions, you're going to have to go and create your own ones of these and wire them in. So that's why I think it's important for you guys to see it. So going back to Ruby land, this is where we were before. Once we've created this request packet, what we have to do is go send it up to the client and sit there and wait. Most of the time when you see client send request, you won't see this extra parameter at the end, which is just an indication of how long we want to wait for that command to time out. And the reason why it's a bit longer with migration is because we're kind of establishing a whole new Meterpreter session, and that could take a little longer than what we would expect. Excuse me. So back into in Meterpreter world now, we've got our dispatcher thread sitting there, and it receives this command. What does it do? So the first thing it does is it reads all of the TLV values out, and from there, because we're actually going to be creating a thread running in a separate process, and those two threads are all going to be vying for control of the communications on that single socket. So we need a synchronization primitive to make sure that only one side is doing things at once. Otherwise, bad things happen. So once that's in place, we then prepare some memory in the target process, which again is like RWX, so that we can copy things over and et cetera. And then after that, the existing process kind of relinquishes control for the other process to take over. And when that's done, it shuts itself down. All right, so let's dive a little bit deeper again. Now, this migration context is just it's a structure that contains a little bit of metadata. Now, if you can imagine, we've got information sitting inside our current process. We actually want to copy some of that stuff over. So the three things that are really important to us when we do this is the handle that we're using for synchronization. So obviously, you can share that handle and you can do signaling. There's the payload, the actual metserve thing itself, because without that, obviously, we're in a bit of trouble. And some information about the socket that we're going to be doing comms on, and I'll get into that in just a minute. The thing that I think is really cool is the abuse of unions in this scenario. So for those people who aren't familiar with C or C++, a union says all of the variables inside this scope can share exactly the same place in memory. So this is like C's equivalent of it can be a duck and a fish at the same time, depending on which value. So I could go e.hEvent, and it'll assume that it's a handle. Or I could go e.bPadding, and it will assume that it's an array of bytes. Now, the reason we do this is because we're going from 32 to 64, or 64 to 32. A handle is actually a pointer size. So in 32-bit land, it's only 4 bytes. But in 64-bit land, it's 8 bytes. So if I send a context over there that is only 4 bytes when it should be 8, Windows gets a little bit upset. Same story with this pointer here to memory. So what we're doing is we're just effectively forcing it to always be 8 bytes so that regardless of the direction we're going in, the structure is the same size and pointers actually make sense. Yeah? Does that make sense? Awesome. Okay, so the migration and shutdown commands are a little bit special in Meterpreter because they need to tell the server when to shut down. So when you've migrated, you need to say, please go and shut down nicely. Same with the typical shutdown command. So you'll see this is an inline request, which implies that we run it on the dispatcher thread rather than kicking it off into a different thread to run as part of the server. So that's how that's defined. Now, the header of this function is not really that interesting except for one thing. Now, this packet here is the structure that contains all of the TLVs. It's what came across the wire when this command was actually invoked. So all those TLVs we poked in on the Metasploit side will appear in this packet. These steps, pretty simple stuff, right? We're just pulling out values. Whoops, we're pulling out values from the TLVs. Unfortunately, C doesn't quite have the nasty duck typing features of Ruby, and so we need to bake the types into the function names because we can't vary based on return values. Okay? So we have uint and boolean and string and all these other bits and pieces. But really all it's doing is saying, for this packet, please get whatever value that's associated with this identifier, which is, in this case, a 32-bit number, and we pull that out and stash it in a local variable. Same story with architecture and payload length and the payload buffer itself. So now we've pulled all the data out of the packet, we can continue on. So the first thing we're going to do is we're going to attempt to get a handle to the process we're going to start migrating to. In order to do that, we actually need a lot of permissions, not just read, write, and a bunch of other things. So this massive bit mask here is saying, these are all the things that I know I'm going to need. If I can't get any of them, I'm not going to attempt to continue. So we call open process with the process identifier we pulled out of the TLV. And if that didn't work, we bomb out. Now, the next thing is kind of specific to TCP payloads only. Because in HTTP and HTTPS, the whole idea of sort of relinquishing comms is pretty simple, right? One just stops and the other one starts polling via HTTP again, and there's no synchronization required. But in the case of TCP, when we're using the socket again, we actually want to duplicate the socket information. Now, I see this context.info value here. This is an instance of that migration context we were looking at before, and the .info is just a blob of space inside that context that's going to contain just socket metadata. So what we do when we migrate, we're going to copy this whole thing over, and we can then create a socket in the other process based on that metadata, and we kind of share socket comms across the two processes. So that's what this is doing. From there, this isn't very interesting either, but creating event, we're creating basically just a handle that we can signal on so that across processes we're able to communicate. But what we need to be able to do is we specify, we create a duplicate handle for this thing. And here you'll see, have I got something in there? No, I don't. These first two parameters here are saying, I want to take this event that is currently associated with this process, and I want to create a handle that works inside this process and store it in here. So straight away, we're taking a copy of what we've got in our current world, and we're putting it in a place where we're going to copy it over to the next process. So from here, we check to see which architecture we're migrating to. I'm focusing again on 32-bit, but it could be 64. And baked in is a blob of shellcode that will kind of handle the case when we're actually kicking off migration, which we are going to dive into in just a minute. Next thing, we're allocating memory. Now, there's some interesting questions around why Windows even creates APIs that let you do this. It's like it wants you to do nasty things. So you can not only open processes, you can allocate memory in target processes, you can write data to those processes, you can kick off threads in those processes. It's like, why would you want to do that? I don't know. There's probably good use cases, and it certainly works for us. So anyway, we allocate some memory, and then we do a little calculation that says, okay, we've allocated memory here, and you'll see for three things. The size of the migration stub, which we're going to look at in just a minute, the size of the migrate context, which has those two unions and the socket info in it, and then the length of the payload. So we've got this big block of contiguous memory that we know we can write all of these things to. And here, the calculation we're doing is we're just figuring out where inside this block of memory we are going to write the metserv payload to, because later on we're going to need to invoke that. Okay? The next step is, all we're going to do is we're going to write each individual component to the appropriate location. So to start with, we write the migration stub first at the start of the memory address. And then after that, we skip that and write the migration context. And then finally, we write the actual payload itself. So that's all sitting in memory now, ready to go. And what we need to be able to do is create a thread. And this kind of sounds simple, but unfortunately it's not. This function, inject via remote thread, what it tries to do is it'll start by hitting a function called create remote thread. And that does exist on some versions of Windows and not on others. It exists on some versions but doesn't work. So behind the scenes here, we try a number of different ways in which to create a remote thread. And if none of those work, which does happen on, say, Windows 2003, we drop through to this thing called APC thread. And this is actually hijacking threads rather than creating new ones. So what it does is it iterates through all of the threads that are running inside that process, and it suspends them. And then based on some pretty basic sort of heuristics, it'll say, I'm going to pick this thread, and I'm going to take its context and overwrite it with information that points to me instead of where it was before. And then we'll just resume every thread in the process and hope it doesn't die. So we can't create a new thread, but we'll take one that's already there and use it for our own purposes. So that's what the APC thread technique is. And I'm not going to dive deeper into that because I know I don't really have that much time. But the two things that are important to note here is that each one of these takes two parameters. The first being the pointer to the allocated block of memory where we've put all of this stuff. And the second is a location from that which points to the start of the migration context, because that is required when we're actually executing our migrate bootstrapper. Okay, so once that's in place and we've actually created the thread, the thread is actually created, resumed, and it is, suspended, and it is then resumed. So we're going to go into the migration stub. I'm not going to show you the 64-bit version because I don't really know how it works. But the 32-bit version looks like this. Let me know when you're finished. Yeah? All good? All right. Yeah, maybe I'm trolling you a little bit. Okay, this is what it actually looks like in source form, which is much better, right? assembly all of a sudden looks really nice compared to the thing that we were looking at before. All right, so this might look a little scary, but it's really not. First thing that we're doing is, so when you call a function, right, function parameters go on the stack. So when this is called, as per normal functionality, the stack plus 4 bytes is actually where the migration context is. So we take that value and we stick it in ESI so that we have a base location that we can sort of offset from to pull out the values like where the payload lives, where the event handles are, and all the other stuff. Okay, so that's what we do first. We then kind of do a little jump from here to here. And the reason we're doing that is because we're leaping over the top of this block API thing, the thing that I mentioned before that Stephen Fewer created. Now this blob of assembly, which again I can't go into based on time, is something that does all that magic hashing stuff that we saw when we did reflective DLL injection. But what it does is it allows us to say, I want these parameters to be passed to a function. Here's the hash of the function. Go and call it. And the block API will go and find the function wherever it is in memory and invoke it. And when it's invoked, control will return immediately back to where you call it from, just like a normal function call. It's genius. You should go and read it if you're looking to deal with sleeping issues. Okay, so here's an example of that call. You'll see pop EBP. The reason why it's doing that is like the return address from making this call is the first instruction to the block API, right? So that's the entry point to the block API's functionality. And so we pop that into EBP, and that becomes our reference point for being able to call block API. So here what we're doing is we're pushing a string onto the stack that contains WS232, which is the WinSock library, so effectively the Windows socket functionality. Push that onto the stack, and then a pointer to that onto the stack. And then we ask block API to call load library inside kernel 32, and that's what this hash is. So you pass that in, block API will go and figure out which function and which module matches that hash. It will then call the function for you. So that's a really cheap way of saying, can you please go and load the Windows socket library for me? Immediately after that, we need to initialize the socket functionality. And it's quirky because in Windows, you can initialize sockets twice and the process is happy. And given that we may have migrated to something that hasn't touched the network for any reason, we need to initialize it just in case it hasn't been done before. Again, otherwise bad things would happen. Okay, what do we got here? So this is the last part of the block of assembly that I'm going to show you. This bit here is creating a call to the socket, WSA socket. WSA socket allows us to create socket handles, and here, really the key thing to note is this offset from ESI is a pointer to the socket metadata that we copied from our existing process. So here we're saying, go and create me a valid socket handle based on this metadata. And from this point, we now have a functioning socket handle in which to do communications. So this is when we say, we stash the socket in EDI. EDI is like the magic socket register. So if you're going to go and create your own stages or any other bits and pieces that kind of resemble this, you need to put socket handles inside EDI prior to kicking off anything Meterpreter related. So once we've done that, we take a reference to the event handle that was also part of our migrate context. That's right at the start of the migrate context. And then we call set event. So on the existing Meterpreter that's running, it's sitting there and it's waiting on that socket handle for a signal. And that's exactly what this is doing. It's saying, okay, we're pretty much set up. I'm executing. I've created my socket. Everything's initialized. You can now shut down. And so at this point, the other Meterpreter is now shutting down. And here, all we're going to do is invoke the payload. So ESI +8, which is 8 bytes, past the event handle, start of the payload. Off you go. So at this point, this is when migration actually completes because the RDI stub is invoked, little bootstrapper is invoked, Met server is reflectively loaded, standard API goes up, priv goes up. Metasploit then pushes up all the extensions that you already had loaded, pushes the port forwards over, just like I said before, and we're basically back to where we started, but living in another process. So that wasn't too scary, was it? It's all good? All right. Now, I don't know how much time I've got left. I think I'm pretty much bang on, but here's the obligatory links slide. So you can find the source of Meterpreter on GitHub. It's not that scary. I promise you, it's really not that scary, except for the Java version. Don't. Go and play with the Java version so that I don't have to. That would be really good. Metasploit framework is in a similar location. Buffett.io is my blog. Metasploit on Freenode is a really good place to go if you want to get stuck into this stuff. Rapid7, I've got to pimp them because they're a great bunch of people. And I had a really good time working with them, though I don't work for them, so I'm not getting any cash or anything for it. And Beyond Binary is my company in Australia, so look forward to your pull requests if you feel gutsy enough to do them. And that's it. Is there any questions? No? All right, so yeah, so you're going to just go away and start. All right, thank you.